Hello, my name is Michelle Chu from the University of Illinois and Chicago, and I'm going to tell you about embedded, totally geodesic submanifolds in small volume cust hyperbolic manifolds. And this is joint work with I want to read. Okay, so let's get started. So the first thing I want to do is I want to set W throughout this talk to be a minimal volume. This is important, so let me just highlight it. Cust, orientable, hyperbolic, and manifold. And the general question that we're going to be concerned with is when can you embed a submanifold into W? And by the submanifold M, I want this to be a closed, orientable, codimension 1 submanifold. So in other words, I want this to be an n-1 dimensional manifold, and I want it to be hyperbolic. And I want this embedding here to be a totally geodesic embedding. Okay, so let's think about what happens in the dimension 2 case. So now here, if we want our W to be a minimal volume cust orientable hyperbolic surface, we have two options. The first option that we have over here on the left is the 3 times punctured sphere. And the second option that we have over here on the right is the once punctured torus. Okay, so it turns out that the 3 times punctured sphere has a unique hyperbolic metric. So let me say that here, this is a unique hyperbolic structure. However, the once punctured torus has a positive dimensional tabular space. So here we have many hyperbolic structures. And in the 3 times punctured sphere, this unique hyperbolic structure, you can see that there are no closed simple essential curves. So once you put in the hyperbolic metric, you'll see that there are no closed embedded geodesics. And however, in the once punctured torus, there are many closed simple curves. Here's an example of one. That's one. If you want a different one, let me draw a different one here. What about in dimension 3? So in dimension 3, the cust minimal volume hyperbolic manifolds. There's 2 of them. The first one, it's a very famous manifold. It's the complement of the figure 8 knot in S3. And it is known to have a hyperbolic structure. And the other one is its sibling. So we don't have a picture of it. It's not a knot complement. But it is another cust hyperbolic 3 manifold. It has the same volume, which is the minimal volume of a cust hyperbolic 3 manifold, same volume as the figure 8 knot. And they're actually commensurable to each other, but sorry, I don't have a picture for it. But in this case, one thing that we do know about them is that these are arithmetic of simplest type. And this is sometimes called standard type or type 1. And what that means is that they have many closed, immersed, totally geodesic surfaces. There's lots and lots of them. There is, in fact, infinitely many. And perhaps you'll hear more about this in Nick Miller's talk, also in this session. However, they do not have any close embedded totally geodesic surfaces. Okay, so let me go back over here to dimension 2. The 3 times punctured sphere, this unique hyperbolic structure, also happens to be arithmetic. And over here for the once punctured torus, well, we know we have many hyperbolic structures, but there are some of those that are arithmetic. Only a few of them. Most of them are not, but some are arithmetic. Okay, so this leads us to ask our question that we have over here, a bit more specifically for arithmetic manifolds. So now we're going to let W be a minimal volume orientable cuffed arithmetic hyperbolic M manifold. And here is the conjecture. If W contains a close embedded orientable totally geodesic codimension 1 submanifold, then it must have been that the dimension was 2, and W was in fact an arithmetic once punctured torus. Okay, so let's talk about some facts. The first fact is that every cuffed arithmetic hyperbolic manifold W, as above, is going to be commensurable to one that looks like this. So this is a quotient of this orthogonal group. So what I mean by this is you take the orthogonal group that is preserved by a certain quadratic form. I mean the identity component of this, and then I'm looking at the elements in there that have integer entries. But it's going to look like some quotient, it's going to be commensurable to some quotient that looks like this, where F is actually an isotropic rational quadratic form of signature N1. And whenever you have this, you get, when you take this quotient, you get something that's cusped. So this quotient might not be a manifold. It can still be commensurable to some manifold. Okay, so this is the first fact that I want to mention. So here's an example of when this happens. So example, if I take F to be the following form, so when I evaluate it at a vector X, I get this. Well, it turns out that if I take this particular form, then if I look at the fundamental group of the figure 8 knot, or the fundamental group of the sibling of the figure 8 knot, or the sister of the figure 8 knot, both of these are commensurable with this orthogonal group. Okay, so that's just one example. Okay, here's another fact. Okay, so now we're still in this case that W is a cusped arithmetic orientable hyperbolic manifold. So now in this case, then every totally geodesic submanifold M of W is also going to be arithmetic. And it also is going to have a corresponding quadratic form. So it might itself not be cusped, but either way, it's going to have a quadratic form. If it's not cusped, then that means that its quadratic form is not going to be isotropic. So it's going to be what we call anisotropic. Okay, and here's a third fact. So Meyer's theorem tells us that every rational quadratic form of rank at least 5 is isotropic. So what does that mean for us in our case? So then let's say here, if Wn is such that this dimension of W is at least 5, and you have M embedding into W, which is codimension 1, then what we know is that M says totally geodesic submanifold, and it's also arithmetic because of fact 2, and it's going to have some quadratic form. So it has its corresponding quadratic form F, which is going to have signature n minus 1, 1, which means that it's going to have rank n minus 1 plus 1, which is at least 5. So now, because of Meyer's theorem, that means that this is isotropic. So what it means is that M must be cusped. So it is not a closed, totally geodesic embedded submanifold. Okay, so the conjecture reduces to dimension 4. Okay. So what are the minimal volume hyperbolic Four manifolds? It turns out this is a difficult question. So here, hyperbolic Four manifolds have positive Euler characteristic, and there's only finitely many that are going to have minimal volume. So, but what is the minimal volume, or what is the minimal Euler characteristic? Well, thankfully for us, Radcliffe and Chance in the year 2000 were able to answer this question for us. So what they did is that they studied certain side pairings of the faces of the ideal 24 cell. Okay, so the ideal 24 cell is an ideal polytope that is hyperbolic of dimension 4, and it has 24 faces. And if you match up the faces in the right way, you might get a manifold. So they looked at this. They didn't look at all the possible side pairings. They looked at a certain class of them. Oh, I shouldn't have put a G here. A certain class of them. And they found 1,171 cusp hyperbolic Four manifolds with Euler characteristic equal to 1, i.e. minimal volume. Okay, but out of this 1,171, which is quite chunky, 22 of them are orientable. So all of the other ones are non-orientable, so they're not ones that we're caring about for in this conjecture. Okay. So this was the first example of finding these cusp arithmetic hyperbolic manifolds of Euler characteristic 1, and taking covers of them, then you can see that in fact that means that you can get all possible Euler characteristic. But let me also say here that all of these all are in the same commensurability class. So this led to the question of whether it must be that all minimal volume hyperbolic Four manifolds have to be in the same commensurability class, but this was recently answered as a no. So let me say here, this is work of Riolo and Slavic in 2019, so this is very recent. So they showed that there is at least one other commensurability class. There is at least one other commensurability class of cusp hyperbolic Four manifolds, which contains, so let's say containing a minimal volume cusp hyperbolic arithmetic Four manifold. Okay. And finally, I'm going to say that Radcliffe and Chance have been studying all other possible side pairings of the ideal 24 cell, not just the particular ones that they studied in their 2000 paper. So they probably have many more examples, but they are not yet available. Okay? Okay, so here is the theorem that I'm going to tell you about. So now we're just going to restrict the case that W is one of those 22 manifolds that I mentioned before from the Radcliffe and Chance paper in year 2000. Okay, so if W is one of those, then we can prove that W does not contain any closed, embedded, totally geodesic 3 manifolds. Okay, so these particular W satisfy the conjecture. And again, this is joint work with Alan Reed. Okay. So how are we going to go about to do this? So the first thing we can do, let's say this is the first obstruction. So if such embedding an M existed, then the first Betti number of the manifold, of W would have to be positive. Okay, and for 7 out of 22 of these cases, so for 7 out of 22 of these, the first Betti number is actually 0. So we know that those satisfy the conjecture, so we don't have to worry about those. So that leaves us with 15 remaining cases. Okay. Yes, so let me say now that this paper where they are described, this paper of Radcliffe and Chance, they're described very explicitly, and it's really nice. And one of the nice things that they say is that, well, all of these have 4 cost-embedded total geodesic 3 manifolds in them. So they're cost, they're not closed, and these embedded manifolds might not be orientable. So here is the idea. Let me draw a picture for you. So here is a picture, or this is a cartoon in dimension 2. So cartoon 2 dimensions down. Say this is our polytope. If we look at this cross section of our polytope and this other cross section of our polytope, so in dimension 4 we're going to have 4 different cross sections. Turns out that when we do this nice gluings that they studied, these cross sections glue up to embedded 3 manifolds. Okay, and Radcliffe and Chance work make it possible to identify what these are. And in these 15 cases, at least one of these is orientable. And let's call this orientable one, let's call it N. So in this picture, let's say we'd have something like this cross section, it glues up to give you N. Okay. So what we're going to look at, well, we're going to assume that we have this other M, which is closed, totally geodesic embedded, and into W. And we're going to ask, how does M meet N? Okay. So Radcliffe and Chance also tell us that whenever N is this cross section that is orientable, it's actually one out of 3 possibilities. And the 3 possibilities are link complements, and it has to be one of these 3 link complements. The first one that I have over here, this one in red, is the Borromean rings. And here you can see the notation in the Rolson tables. The next one is this other orange or yellow link, or otherwise it's this green link over here. Okay, So one thing that we can show is that, well, M actually never meets N. But if it did, then their intersection within W would be a closed embedded total geodesic surface. S, which would embed totally geodesically into both M and N. And what we can do is that we can show for these particular three link complements is that we show that there does not exist a surface that embeds into N totally geodesically. Okay. So now we go into two different cases. Well, we know M doesn't meet the particular cross-section that's orientable. There's three remaining cross-sections, and some of those might be non-orientable. So the first case is to consider M that does not meet any of the cross-sections. Okay, so one other nice thing about the fact that these are cross-sections, let me say this here, is that they also happen to be reflection faces. Okay, and here is, again, going back to this cartoon that we had over here. Well, here is one of the cross sections that we called N. Here's another one, let's say we call it M prime. And if I have M and I know it doesn't meet any of them, well, I know that it would have to be like somewhere over here, okay? But these reflection faces tell me, well, there's another copy of it over here, and another copy of it over here, and again, another copy over here. So, well, this was a picture in dimension 2. If we think about doing this again, but in dimension 4, this tells us that actually there are 16, say this here, we get 16 disjoint copies of M embedded in our manifold W. And here, what we're going to use is we're going to use some volume bounds of Basmangian to say that now this is not possible. So he gives volume bounds for the tubular neighborhoods of closed embedded totally geodesic hypersurfaces. So what that means is that, well, around each one of these, there's the neighborhood. These neighborhoods are disjoint from each other, and they contribute some amount of volume to the manifold W. And this volume grows as the volume of M as a 3-manifold grows. So what we end up having is that then the volume of our manifold W would have to be greater than or equal to 16 times this volume bound that we get from Basmangian, corresponding to the volume of this manifold M. But this is enough to give us a contradiction, because even if we put in the smallest volume hyperbolic 3-manifold into this volume bound from Basmangian, this is too large. So this is contradiction. Because this has to be minimal. Okay, so that was the first case. So now let's look at the second case. Well, again, remember there's at least one cross section which is orientable, and we already showed that that M does not meet that one. But what if it meets some non-orientable cross section? So here, let's draw again the same cartoon let's say this one here is n, the orientable one that we know it doesn't meet. And here, let's put some other one that it probably does meet. So then m would have to meet at something like this. Okay, but now we can reflect in n, so there's at least 2 of them. So we have something like this sort of picture. However, note now that m, it's meeting this n prime. So it's meeting over here in a surface here. Let's call it S. So what I'm saying now is that I now have this totally geodesic surface that embeds into both m and n prime. Okay? And what I'm going to use here to obstruct this from happening is a result of Kojima and Miyamoto. So what they looked at is at volumes. Oh, let me again say when this is from. So they looked at volumes of hyperbolic 3 manifolds with totally geodesic boundary. So this is what would happen if you say take M and cut along S. And this ends up giving us a lower bound on the volume. So this is the 3-dimensional hyperbolic volume of M, which now, oh, sorry, this should have been down here. And now if I combine this with the Basmantian bounds, then we again get a lower bound on the volume of W that is twice times this bound we get from Basmantian related to this manifold M. But combining these 2 results, this is again a contradiction. Okay, thank you.